Remind me, because just now got some problem. I forgot the mic problem. Yeah, just remind me if I forgot.你还在解哪一个？
没有，
没有在解。没有，我说你平时还在解那个，写出来了吗？没有，没有写出来，你还打算写哪个？写得出啊？没有啊？你说他对你要证明给我看的。
就是说工具吧，就是我找不到反例，我就是反例，就是
哪来？
在想象。
还没解吧？还没解。
就跟那个一样。
后来我找。
表示通过
对
这个都是人类数据而
对，
感觉特例就
不好有没有？
啊是
OK，应该是
觉得好像都是考我身
没有他的其他的 project
嗯，
怎么办？
那比例今天运算应该行。
basis
就是我感觉
basis of sequence。这个一般这种可以解到那个题目。
两个不同两个分做个 sequence 中，这个 sequence 怎么接？他们这个 sequence 的合都是。
呀，但是问题是你怎样造出那个不 conversion 模式啊？那个不是重点哎，
人家是重点。
自己那个重点这样。要 squeeze 两个 conversion 的东西，然后又 limit 去每一个 term 也 limit 去零，然后能不能造出一个 limit 去零的东西？但是加在中间的是 limit 去零它每一个 term，但是它 diverge 吗？diverge 不一定要加到 infinity 那个东西，它 doesn't exist 也是可以啊啊，有可能吗？感觉不是可能。
刚刚那个
什么？
fx 在 x 轴 approach 2，y 轴 approach 2，那怎样解释？最后
解释就是我要全部 path 才行啊，那个只有两个 path。对，哦，我没有写出来，
你还没有解释哦。
还没有写出来。我还没有做结论哦，
啊，
应该是 no，因为我们要 check for all part，我应该要做一个结论。对啊，no no no，但是 no 等一下我再做一个结论一下，忘记做这个结论。没有，有没有一个东西是 limit 去零，但是你加的时候，它的 partial sum 的 limit 它是 exist，能不能一直加很小的东西，但是呢，它的 partial sum 又不 exist，有可能这样的事情。Hello, okay, testing. So, just now for this limit, right, we haven't write down the conclusion, although we just keep mentioning. So, if you just prove that there are two paths you take, okay, fxy approach 2 is not enough to deduce the limit of the function of two variable also approach 2, because you need to take for all paths. Okay, so the answer is no. We cannot conclude it until we tested when we have until we show the limit the limit, okay, we show that the functions approaches 2 from all directions. Okay, from all directions we have to show. Okay, later we will see this example. Okay, we will see example soon. How we gonna consider all direction? How we gonna consider all direction without using epsilon delta? Okay. Okay. So this is the technique. Okay, so this is the technique. We have learned polar coordinate, right? So we need to make use of polar coordinate. So let's compute this limit here. Okay, you see there's so many square here, right? So polar coordinate, play around with circles. Okay, so maybe we'll use polar coordinate here. Maybe you can use other method, but we want to use polar coordinate for this example. So let's use polar coordinate. See how it makes things easier. So what's polar coordinate again? So how you transform xy into r and theta. As how you transform xy to r and theta. How? Which one is equal to r cos theta? X is equal to r cos theta. Y is equal to r sine theta. So this tells you that every point lie on the circle of radius r centered at 0, 0. Okay, so this equation tells you that every point lies on a circle that is centered at 0, 0, the origin, with radius r. Okay. Okay. Chiffon, okay. Okay. I see confused again. Okay. So how? Okay, right. Sure, cool. So how you relate r with xy? So really, because it is lying on the circle of radius r. So because xy are lying on the circle of radius r, so in particular xy satisfy s squared plus y squared equal to r squared. Or r is equal to the square root of s squared plus y squared. So this is the radius. So meaning what? So if you approach from any point to the origin, right? Okay. So you are approaching from the every angle. So in particular, you are approaching from every angle. So your radius is going from positive to 0, right? So, okay, let me write down. Let me draw it. So you are approaching 0, 0 anywhere, right? Okay. In particular, if you look at the circle here, this radius is getting smaller and smaller. Okay. So when you consider the radius, you consider all paths going to 0, 0. Okay. Okay. So does this make our function looks nicer now? So let's see. So our function is going from the xy to the origin, sine x squared plus y squared over x squared, 3x squared plus 3y squared, which is what? Okay, so we change variable from xy to r theta. X squared plus y squared is just r squared. And then at the bottom, we get 3 times r squared. And the limit changing from xy to r, we decided our radius is going from the positive part to 0. Okay, so how to solve this limit? What's this limit here? What's this limit here? So what's the limit of x going to 0 for sine x over x? What's this? Huh? 1. 1. So how you prove it? Theorem? Do you need theorem? L'Hopital rule, you can do it. You can use L'Hopital rule. Maybe you can create a theorem, but you can use L'Hopital rule. Use L'Hopital rule. Yeah, question. Sorry. Okay, L'Hopital rule. L'Hopital rule. Okay, what does this mean? This means that when you get close to 0, right? So this sine function is really the same as the x equals to y function. Okay, when you get close to the origin. This is kind of important. Improve, right? You also need to need this thing quite frequently. Okay, so you need to know that or remember that sine x is really close to y equals to x when it is close to 0. Okay. So what do we get for this? This is 1/3 times 1, which is 1/3. Okay. So in this case, the limit exists because we count it from every direction. Okay, we count it from every direction, all the direction, the radial direction. Okay, so how about we try this polar technique on this question here? Okay. So let's try the polar technique on this question. So this, after change of variable, this part here will become r go to 0 plus. Okay, xy is what? R cos theta times r sine theta. Okay, over r squared. Okay, so what do you get here? So what you get here is cos theta sine theta, right? So what's this limit equal to? 0? Why? Yeah, okay. So this is a function in theta. So nothing in r, right? Okay, so what is this? This is just cos theta times sine theta. So what does this mean? What does this mean? If you take different angle, you will get different value. Okay, so different angle become different values. So what does it mean? So the actual limit doesn't exist. Actual limit doesn't exist. So the actual limit doesn't exist. Okay. So strictly speaking, right? Strictly speaking, we cannot write equal here, right? Okay, because it doesn't exist. But this is just for calculation. So strictly speaking, it doesn't exist. Should I plug in? What time is it? Okay. How about, let me see. Can you try one question? Try, see which one is good to play. How about try this? I let you try this. Let you practice the polar method. Huh? Use polar. Let me try this. Done. Okay. So some of you done. So let's try and substitute the polar coordinate, right? And so like what we said just now, right? Strictly speaking, we can't write equal, but we just do it for the sake of computation, where we get 3r cos theta squared r cos sine theta r squared. Okay. After cancellation, what do you get? 3 times r cos square theta sine theta, which is just 0. Okay. So what whatever direction you take, okay, it is going to be 0 when you take the limit. Can you take the left limit of 0? I think, wait, let me think. I think you can, but it's equivalent. So right limit just means what? You approach 0 from the right. So meaning you approach from the positive number. Oh, right? Because you are going from far away and then you come close to 0. The radius becomes 0. Of course, you can take 0 minus, but in radius, in polar coordinate, you can turn the minus radius to, yeah, just change the angle, right? So it's equivalent.
So actually, left limit, right limit, and all is equal.
The right limit and the left limit and okay. So no left and no right, meaning when left and right equal, only you can write the no, yeah. So just left and right. Yeah, so I mean, when left and right equal, only then you can get rid of the left, right? Okay, so I mean, in polar coordinate, right? Really, you are going one way only, isn't it? Okay. You just think of it. You are away from the origin, so you are positive distance. So you want to come close to this distance, you just reduce your radius. But if you really want to talk about 0 minus, also can, because in polar coordinate, we consider minus radius theta equals to r theta plus pi. Yeah. So you can just turn it to positive radius and then look from there, see from there. So it's really the same. Yeah.
Basically, get negative or positive or carry on positive negative that the
Doesn't matter.
result will be the same.
Yeah. Yeah. The result will be the same. Yeah. The result will be the same. Yeah. Okay. But I think positive nicer. Yeah, because meaning you're shrinking your path. Shrinking your path. Okay? Shrinking your path. Okay. Another way to solve this question, right? You can solve it using a higher dimensional squeeze theorem. Okay, so you can use squeeze theorem to solve it. So to use squeeze theorem, right, you need to make sure the function is squeezed by two functions that limit to the same point. Okay, so how to squeeze it? So this function can be squeezed in between 0 and 1 for x squared over x squared plus y squared. Okay, first think about this question first. Does this make sense? Yeah, makes sense, right? Because y can take what value? Infinitely many value. Okay, but y squared only produce positive value. Okay, so you can for y squared really live in where? Live in 0 to infinity. Okay, so when it is 0, it is just x squared over x squared, which is 1. So when y squared increases, the denominator increases, so you get number less and less and less and less and less. Okay, makes sense? Okay. So, but this is not quite our function yet, right? So we just multiply 3y to the inequality. Okay, now we will decide whether this is a good bound or not. So what's this bound? So on the left-hand side, when you take xy to 0, because this is just a constant function, we always get 0. Always get the constant, which is 0 in this case. And then if we take xy to 0, 0 for 3y, what do we get? We get 3 times the limit of xy go to 0, 0, y, which is, just now we learned from the theorem, say that this is 0, which is 0. 3 times 0 is 0. Okay, So by squeeze theorem, higher dimensional squeeze theorem, the limit of xy going to 0, 0 of the original limit, original function 3y x squared over x squared plus y squared is equal to 0. Okay. Okay, Jimbo. Okay. Yeah. Okay. Yeah, different way to getting the same limit. This is good. So it's good that if you get approach one question from different way of seeing one question. Okay, next, continuity. So just now we touched on it a little bit. So to say that fxy is continuous at a point AB, okay, we require that f has a value at AB. Okay, so f evaluate at AB, you have a value. Okay, then you compare this value with your limit at that point. Okay, limit at that point mean you consider the neighborhood around AB. Okay, the neighbor around AB. Arbitrarily close to AB, the point that are arbitrarily close to AB. And then look at the f, and then look at this limit compared to the value at AB. If the value of f at AB is equal to the limit there, which is limit of fxy when xy approach AB is equal to fab, then we will say that this function is continuous. Okay, this one, okay, sink in already. So this idea need to sink in to your mind. Okay, next, composite function. Actually, we already used this fact, even though we haven't mentioned it yet, but we will mention it formally now. If a function g of two variables is continuous at AB and a function f of one variable, wait, this one, okay, one variable is continuous at GAB, then the composite function f composed with g defined by fg apply on xy, which is fgxy is continuous at AB. Okay, in fact, this one works for I think any generality. Okay, as long as the composite makes sense. Okay, so you see that what is happening here? Okay, what is happening here? So let's lay out what is happening here. So G is going from R2 to R, right? So F is a one variable, one function of one variable. Why? Because you want to compose G before F, right? So G go from R2 to R, and then F move from R to R. Okay, make sense? So this part, this so let me put it here. So this long arrow here, we will denote as F composed with G. Okay. So what is F composed with G? Okay, so why we write this equal signs here? All right. So we need to evaluate G at XY first, and then give you a number, right? And then you evaluate your F at that number, and then you get another number. Make sense? Okay. So you got XY, and then split out a number. Okay, let's call it maybe Z. And then you apply F on Z again. You get another number. Let's call it P. Okay. So this is also equal to F apply on GXY. And then this is very important. This is very, very important. Then we define this thing as F composed with G. Okay. Make sense? Okay. So actually, before I say all these, right, this thing doesn't make sense. Okay, this is a definition. This is a new definition when you compose two functions. Okay. At first, you only know how to evaluate a function at a point. Okay. So this is the definition of F composed G at the point at the point x1. So let me move the wording down. So this is a very important definition. Okay. So this is how we define the composite of function. Okay. So where are the following functions continuous? Okay. So for example, let's look at the function fxy. 2x plus 2y over y minus 4x squared. Where does this function continuous? Where does this function continuous? Where does the numerator continuous? Everywhere. Okay, everywhere you can get a number. How about the bottom one? Where does the bottom function continuous? You sure? I mean just for denominator itself. Everywhere also. Okay. But now you put them together. Okay. I think you don't talk about continuous first. Talk about define. Where does this function define? Make sense, right? Does it make sense if y equals to 4x squared? No, right? Okay, so what you need to make sure for this function to be defined, don't talk about continuous yet. Talk about definers first. So this is defined where y is not equals to fx squared. Okay. So this is the natural domain. The natural domain is where xy such that y not equals to fx squared, 4x squared. So what is y equals to 4x squared? It is a parabola. Okay, so it is defined away from this parabola. Okay, so if it is defined because both of them are continuous at everywhere, so it is continuous everywhere except on the parabola. Okay, so fxy is continuous away from the parabola. So how we write this? So it's the set of xy, okay, in R cross R, such that x y not equal to 4x squared. Okay, makes sense. Okay. Okay. How about the next one? Where does the term inside the cos define? Everywhere also. Okay, cos also defined everywhere.
Yeah.
Okay, so this is the composition of a polynomial with a trigo function, right? Okay. So does this function continuous? Why? Okay, okay. I mean the idea is correct. So now you need to learn the language now. So what is inside, what is outside? What is inside, what is outside, right? Okay, so this is called the composition of function. Okay, since the function inside is continuous, okay, and cos is also continuous, so the composite of these two functions is continuous, okay, by the theorem. So this is continuous because this is a polynomial. Okay, so polynomial continuous at everywhere, right? Actually, any dispute, if I say polynomial is continuous everywhere, you should how to say, challenge this, right? Why polynomial is continuous? I'll let you think about it first. Okay. Yeah. Because what? We don't learn multiply of two continuous functions. We don't learn that product of two continuous function is continuous, right? Doesn't cut. Doesn't mean cut off. Yeah, of course. But I mean, how you formally prove it? Can you formally prove it? Right. Can you formally prove it? Being a composite, so the conclusion is being a composite function of continuous functions, f is continuous. Let me move this. Maybe I can put more detail here. So being a composite function of continuous function on R2, okay, f is continuous on R2. Okay. Any question? Wait, yeah. Sorry. Okay. We do the next part. Let me see. You can look at this first. Let me see if we want to do it or not. I think this is a good example. Let's do this. Okay, I think we saw this, right? So just now we say that have we solved this limit before? Yeah, we saw this limit before. Okay, we proved that this limit, when you approach 0, 0, it is just 0. Okay, so but when I talk about function, right? This function here is okay. Let's call it g for this moment. I want to call this function I'm talking about 3x squared times y over x squared plus y squared is g. So this function, we learned that the limit of this function going to the origin is just 0. Okay, just now we have shown it a few moments ago. Okay, so does this function achieve any value at 0, 0? You get 0 over 0, right? Okay, so you can't really make sense of that number yet. Okay, but like what I said just now, we can fill this hole in. Okay, we fill this hole in just by letting the value to be 0 at 0, 0. Okay, I don't get this 0 by substituting the number. I just force it to be 0 at that point. Okay, now we will see that whether this action makes sense or not. Okay, I force it to be 0 at that point. Okay, so we have limit towards 0, 0 is 0. Okay, and then we force our new function fxy to have a 0 at that point. So you have limit to 0, and then you have 0 at that point. So they are equal. So the limit to the origin is equal to the function at that point. So our new function defined is continuous. Okay, so let me write down. So since okay, so this is a new function we define, right? So this is a new function. So since the limit of fxy go to 0, 0 of fxy equals 0, okay, and we have f0, 0 equals 0 piecewisely. So we define it piecewisely. Do you know piecewise? Piecewise function. So we define this piecewisely. Define piecewise. Okay. Everything non-zero, we use this function. everything not equal to origin, we take this function as a function we take this function, and then at the 0, 0, we just take the constant function 0. And this is equal to piecewise. Then we have, by definition of continuity, the new function fxy is continuous at the point 0, 0. Okay. So since the limit exists, we can just fill in the blank. It's not like the previous example we saw. When x direction you got 1, y direction you got -1, then you cannot fill. Okay. Okay. So before we stop, right, let's introduce one definition. Let you ponder upon. Then next time we'll do example. So suppose. So now we will go into partial derivative. Okay. So partial derivative, you need the notion of limit. So we do it after we introduce the limit. Suppose f is a function of two variables. If y is held constant, say y equals to b, then fxb is a function of a single variable. Does it make sense or not? Held constant b, okay. So you should have at least one example in your mind. Two function variable. Let's say we put it y equals to 2. So this become a 2x. So become a one variable. Okay, function. Its derivative at x equals to a is called a partial derivative with respect to x at ab. Is denoted by f subscript ab, which is the limit of h go to 0 of f a plus h b minus f a b over h. Does this definition make sense or not? Makes sense, huh? Okay. So in the one variable case, right? What do you take? Okay, you take what? What's how to find this gradient here? Is y1 minus y2 over x1 minus x2. Right or not? Okay. But in this case here, we use A as a reference point. Meaning, for example, we can use y1 as a reference point. So what is y2? So maybe y2 is just h away from y1. Okay. And then what? And then x1 minus x2 is just a distance. So let me see. Can I write something better? So let me write better and then we'll finish here. So let's say let me move this. Do you guys have class after this? What time? 6. Okay, I'll finish soon. So let's fix our distance as h, and then this h will get dependent on our y, our h. Okay. So that's why we can just study this version instead of y1 minus y2. You also can phrase this into y1 minus y2. Okay. So for example, I can phrase this limit in this way. So I phrase it as xy going to ab of fxy minus fab over, okay, xy minus a. Maybe we need to take the length here, so I need to take the length function. Okay, so these are two equivalents where similar to what we did in the one variable dimension. Okay, so you should familiarize yourself with these two definition here. Okay. Okay, any question? Any question? So really here, since we already fixed y equals to b, so here is just b. Okay. So since this is just the length of xb minus ab, right, is just the length of x minus a. so we can reduce this further. If you cannot follow, right, I want you to think about this thing. Okay, I want you to think about this. If you still cannot get it, we can settle it next time. Okay. Yeah. Okay, so we will stop here and then we will continue with examples on Friday. Okay.